Let's dive right into this explainer and totally dismantle what you think you know about the shape of our planet. I mean, in casual conversation, we treat the Earth like a perfect sphere, right? Kind of like a flawless billiard ball floating in space. But in the world of precise general navigation, assuming the Earth is perfectly round will quite literally send you miles off course. Today, we're exploring the fascinating mathematical reality of our imperfect world and breaking down the exact formulas and rules that modern navigators use to conquer it.
So why is the shortest path on a map almost never a straight line? Well, what's really fascinating here is that the answer lies in the fundamental flaws of how we visualize the Earth. You see, when we take a three-dimensional, slightly distorted globe and flatten it out onto a two-dimensional chart, we create incredible mathematical distortions. That means the straight line you draw with a ruler on a standard map, it's almost never the actual fastest way to get from point A to point B in reality. To understand why, we really have to look at the true physical shape of our home.
Here's our flight plan for today. 1. The squished Earth reality. 2. Navigating the global grid. 3. The 60-minute rule. 4. Mastering the departure formula. 5. Geocentric versus geodetic latitude. And 6. The shortest path home.
Section 1. The squished Earth reality. First things first, we've got to bust a massive myth. The Earth is not a perfect sphere. It's actually an oblate spheroid, basically an ellipsoid.
The magic number you absolutely need to know here is 21.39. See, because the Earth is constantly spinning, centrifugal force is literally pushing the mass of the planet outward at the equator. It makes the Earth, well, kind of fat in the middle. The equatorial radius, what we call the semi-major axis, is about 6,378 kilometers. But the polar radius, the semi-minor axis, is only about 6,356 kilometers. That's a difference of exactly 21.39 kilometers, or about 11.55 nautical miles. We are quite literally living on a squished sphere.
And because of this bulge, the actual physical length of a nautical mile changes depending on where you're standing. A nautical mile is officially defined by 1 minute of arc of latitude, but since the Earth is flatter near the poles, a minute of arc stretches over a longer physical distance. Think about this, a nautical mile is actually over 6,100 feet at the poles, exactly 6,076 feet at 45 degrees north or south, and it shrinks to less than 6,050 feet right at the bulging equator. Modern navigation systems naturally compensate for this, but older manual systems actually had to factor in this latitude error.
Moving right along to Section 2, Navigating the Global Grid. Now that we know we're dealing with a squished, bulging planet, how exactly do modern systems, like the super common World Geodetic System of 1984, or WGS-84, actually plot coordinates across this odd shape?
To get around this grid, you absolutely need to understand two very distinct types of lines. First up, we have great circles. These represent the absolute shortest route across the surface of the Earth. If you're flying long haul, you definitely want to be on a great circle track. Second, we have rhumb lines. These track along parallels of latitude, meaning they maintain a constant heading, like flying exactly 90 degrees true for due east. But here's the catch. Aside from the equator itself, a rhumb line is never the shortest route.
Which brings us to a fascinating mathematical quirk about our lines of longitude. All meridians run pole to pole, right? Originating in the south, shooting toward true north. Because they wrap directly around the Earth's center, every single meridian is a great circle. But because following a meridian means keeping a constant heading of either due north or due south, they are simultaneously rhumb lines. They are essentially the mathematical unicorns of our global grid.
All right, Section 3, the 60-minute rule. We're getting into high-stakes territory now, so definitely pay close attention. If you're a student, this is where you avoid the single most brutal trap in exam calculations.
Before you even touch a calculator to find the distance between 2 points, you've got to burn this fundamental rule of thumb into your brain. If your two positions are in different hemispheres, say one is north and one is south, you add the coordinates together to find the difference. If they're in the same hemisphere, you subtract them. This applies to both latitude and longitude. Just always visualize the equator or the prime meridian in your head to double-check your logic.
Now for the actual math. And this is it, the absolute #1 trap for students. You cannot, under any circumstances, treat coordinate minutes like base 100 decimals. There are 60 minutes in a degree, not 100. So if you need to subtract a larger minute value from a smaller one, you absolutely must use the 60-minute borrowing rule. You borrow 1 full degree, which immediately magically turns into 60 minutes, and then you add those 60 minutes to your minute column before you do your subtraction.
Seriously, treating minutes like decimals will totally wreck your entire calculation. Picture this. You're at 87 degrees 13 minutes, and you need to subtract 26 degrees 37 minutes. You can't just subtract 37 from 13. Instead, you borrow 1 degree from the 87, dropping it down to 86. That borrowed degree becomes 60 minutes. Add that to the 13, giving you 73 minutes. Now you safely subtract 37 from 73 to get 36 minutes. It's a really simple mechanical step, but forgetting it is literally the most common mistake made on navigation exams.
That brings us to Section 4, Mastering the Departure Formula. Let's take our grid and our precise new math rules and actually calculate distances along the Earth's curves.
There's actually a secret little mathematical formula that explains exactly why the east to west distance between two meridians practically vanishes as you fly toward the poles. We call this east-west distance departure. Because meridians converge at the poles, a single degree of longitude is 60 nautical miles wide at the equator, but 0 miles wide at the poles. To find the exact distance anywhere in between, you multiply the change in longitude, which has to be in minutes, by the cosine of your current latitude.
So calculating your departure spits out the physical east-west distance in nautical miles. But, and this is a big but, remember our rule about great circles versus rum lines from earlier? Unless you are sitting exactly on the equator, this departure distance is along a parallel of latitude, meaning it is not the shortest distance between those 2 points. It's simply the distance if you flew a constant heading.
Section 5. Geocentric versus geodetic latitude. Let's push just a bit deeper here and see how our squished Earth complicates the very definition of a coordinate itself. Because our planet is an ellipsoid and not a perfect sphere, if you were to draw a plumb line straight down into the dirt beneath your feet, it wouldn't actually perfectly intersect with the true center of the Earth. And this gives us 2 totally different ways to measure latitude. Geocentric latitude is measured precisely from the Earth's core. Geodetic, or geographic latitude, is measured from that perpendicular plumb line dropping right off the surface. Because of that equatorial bulge we talked about, these 2 measurements create a very real error. On a perfect sphere, these lines would be identical, but on our ellipsoid, they completely diverge. The greatest difference actually happens right at 45 degrees north or south, amounting to an 11.6-minute difference in arc. And because we navigate on the surface, your aviation charts and modern GPS systems actually plot the geodetic, plumbline coordinates, largely ignoring the geocentric ones.
And finally, Section 6, the shortest path home. For our last calculation, let's look at the absolute extreme. We're talking about navigating right over the top of the globe where standard coordinate directions literally start to lose their meaning.
Imagine you need to find the distance between 2 points on exactly opposite sides of the Earth, like a meridian and its exact anti-meridian, which always add up to 180 degrees. Well, the absolute shortest path is straight over the pole. You bypass the departure formula entirely. Instead, you find the angle from your first point to the pole, find the angle from the second point to the pole, and just add them together. Multiply those total degrees by 60, and boom, you've got your exact distance in nautical miles directly along the curvature of the Earth.
So if your GPS failed directly over the North Pole, could you manually calculate your way home? Understanding this math isn't just about passing an aviation exam. It's about trusting the physical reality of our squished Earth when the computers go dark. We rely so heavily on automated systems that instantly run these departure formulas and WGS-84 ellipsoid models. But knowing exactly why a nautical mile stretches at the poles, or why you absolutely must borrow 60 minutes instead of 100, really grounds you in the true physical shape of our world. So I'll leave you with this. If all the screens went black and you only had a paper chart and a pencil, would you know how to draw the curve that brings you home?